What if everything we see, every star, every planet, even the empty stretches of space, is just the surface of something far deeper, something invisible yet everywhere? Picture this: beneath the fabric of reality, hidden fields ripple and pulse, shaping the universe in ways we're only beginning to grasp. These aren't just abstract ideas scribbled in a physicist's notebook. They could be the unseen architects of existence itself, quietly orchestrating the laws that govern everything from the birth of galaxies to the spin of an electron. And the craziest part, we might be standing on the edge of uncovering them. For centuries, humans have looked up at the night sky and wondered, what's really out there? But what if the answers aren't just in the distant glow of stars, but in the invisible threads woven through the cosmos? Hidden fields, as scientists call them, are like the backstage crew of the universe. You don't see them, but without them, the show wouldn't go on. Think of gravity, electromagnetism. These are forces we've mapped, forces we can measure. But what about the fields we can't? The ones that might explain dark matter, dark energy, or even the very nature of time. That's where things get thrilling. Because if these fields exist, they could rewrite our understanding of reality itself. This isn't just science fiction. It's the cutting edge of physics, where theories like quantum fields, extra dimensions, and cosmic inflation collide. Imagine a universe where every empty space teems with invisible energy, where particles pop in and out of existence like bubbles in a vast, unseen ocean. It sounds wild, but it's the kind of wild that could be true. And today, we're diving deep into 30 mind-bending theories about these hidden fields, ideas that stretch from the edges of black holes to the first moments after the Big Bang. Some might turn out to be dead ends, others could unlock secrets we've chased for generations. So buckle up, because the universe is far stranger, far more mysterious than we ever dared to dream. And the adventure, it's just getting started. If you could zoom in on empty space way past atoms, past electrons, you'd find it's anything but empty. Even in the deepest vacuum, the universe is fizzing with activity, a subatomic dance of particles blinking in and out of existence so fast we can barely detect them. These are quantum vacuum fluctuations, and they're not just a quirk of physics. They might be the first clue to hidden fields that shape reality itself. Picture a calm lake at night. On the surface, everything looks still, but beneath, currents swirl, fish dart, and unseen forces tug at the water. The quantum vacuum is like that. What we call empty space is actually a seething sea of virtual particles, pairs of electrons and positrons, quarks and antiquarks, popping into being and vanishing in fractions of a second. They're called virtual because they don't stick around long enough to measure directly, but their effects, those are very real. When two metal plates are placed incredibly close together in a vacuum, these fleeting particles push on them with detectable force, an experiment known as the Casimir effect. It's proof that so-called nothingness is alive with energy. Now, here's where it gets wild. Some physicists believe these fluctuations aren't just random noise. They could be ripples in a deeper, hidden field, an invisible structure that permeates everything. Think of it like gravity's unseen pull, but far stranger. This field might subtly nudge particles, tweak the laws of physics, or even explain why the universe is expanding faster than it should. Dark energy, that mysterious force driving galaxies apart, could be tied to this hidden background hum. And then there's spacetime itself. Einstein showed us it's flexible, bending under mass and energy. But what if those quantum fluctuations are constantly warping it on the tiniest scales, like invisible fingers dimpling the fabric of reality? Some theories suggest these tiny distortions could accumulate, creating strange effects like particles appearing to teleport or time flowing unevenly in ways we haven't yet detected. The craziest part, we're just starting to scratch the surface. If hidden fields are real, they could rewrite the rules we thought governed existence. From the way stars form to why matter outweighs antimatter, these unseen forces might hold answers to questions that have puzzled us for centuries. So the next time you look up at the night sky, remember, the true mysteries of the cosmos might not be in the distant stars, but in the humming, flickering void between them. The Higgs field isn't just a scientific concept, it's the invisible sculptor of reality, the reason particles have mass at all. Picture this: every particle in the universe, from the quarks in your body to the heart of a distant star, moves through an unseen cosmic molasses. That's the Higgs field. Without it, electrons would zip through space at the speed of light, atoms could never form, and the universe as we know it would simply fail to exist. But here's where it gets even more fascinating. The Higgs field might be just the beginning. What if there are other hidden fields, similar yet different, quietly shaping the cosmos in ways we haven't even imagined? Some physicists speculate about additional scalar fields, cousins to the Higgs, that could explain mysteries like dark energy or why the universe is expanding faster than predicted. These fields wouldn't give particles mass but might influence the very fabric of spacetime itself, stretching it like an invisible hand tugging at the edges of existence. Take inflation, for example. In the first sliver of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. What fueled that explosive growth? One leading theory points to a hypothetical inflation field, a kind of cosmic engine that revved up spacetime before fading away, leaving behind the universe we see today. If such a field existed, its echoes might still linger in the faint ripples of the cosmic microwave background, the afterglow of the Big Bang. And then there's the possibility of quintessence, a dynamic field that could explain dark energy's grip on the cosmos. Unlike the steady hum of the Higgs, quintessence might shift and evolve over time, its energy waxing and waning like a cosmic tide. If true, it could mean the fate of the universe isn't set in stone. Expansion might slow, reverse, or even tear spacetime apart in a distant future we can barely comprehend. What's remarkable is how these ideas connect. The Higgs field explains the tangible, why things have weight and structure, but these other fields, they could hold the keys to the intangible, the acceleration of galaxies, the birth of the cosmos, even the arrow of time. Together, they paint a picture of a universe far richer and more layered than we ever suspected, where every empty space hums with unseen forces, quietly writing the rules of reality itself. Dark energy, the mysterious force accelerating the universe's expansion, might not be the static, unchanging presence we once assumed. What if it's alive, shifting, evolving? Imagine a river that suddenly speeds up, slows down, or changes course without warning. That's the provocative idea behind dynamic dark energy, a theory suggesting this cosmic force isn't just a fixed backdrop but a field in flux, pulsing with unseen activity that could rewrite the fate of everything. For decades, scientists treated dark energy as a constant, represented by Einstein's cosmological constant, a steady pressure woven into spacetime itself. But observations of distant supernova and galaxy clusters reveal puzzling inconsistencies. The universe's expansion rate doesn't quite match predictions, as if dark energy's strength has varied over cosmic history. This has led some researchers to propose an alternative, quintessence. Unlike a static force, quintessence is a dynamic field that could grow stronger or weaker, its energy ebbing and flowing like an invisible tide. Think of it like this: if dark energy were a dimmer switch rather than a fixed light, its subtle adjustments might explain why the early universe expanded slowly before suddenly accelerating. Some models even suggest this field could interact with other fundamental forces, momentarily tugging at the fabric of spacetime in ways we haven't yet detected. The implications are staggering. If dark energy isn't constant, the universe's ultimate destiny, whether it tears apart in a big rip or crunches back into a singularity, might hinge on this hidden field's unpredictable behavior. Here's where it gets stranger. dynamic dark energy could be tied to entirely new physics, perhaps an undiscovered force or a higher dimensional phenomenon leaking into our reality. Some theories speculate that it's connected to the same quantum fields responsible for inflation in the universe's first moments. Others propose it's a sign of dimensions beyond our own, where hidden forces ripple into our cosmos like vibrations from a parallel world. The hunt for answers is already underway. Telescopes like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope are mapping the universe's expansion with unprecedented precision, searching for tiny variations that might betray dark energy's true nature. If they find evidence of a dynamic field, it would be one of the greatest revolutions in cosmology since Hubble discovered the universe was expanding. We'd be forced to confront a cosmos far more restless and alive than we ever imagined, a place where even the vacuum of space hums with hidden change, quietly steering the destiny of galaxies, stars, and time itself. Among the most tantalizing candidates for dark matter are action's hypothetical particles so lightweight they barely register, yet so abundant they could form vast, invisible fields stretching across the cosmos. Unlike the heavy, sluggish particles once thought to make up dark matter, actions would be ghostly, slipping through ordinary matter as if it weren't there. But don't let their delicacy fool you. If these particles exist, their collective behavior might weave the very fabric of dark matter itself, solving one of astronomy's greatest mysteries. Imagine a cosmic ocean, not of water, but of ultra-light actions vibrating in unison. On their own, each particle's influence would be vanishingly small. But together, trillions upon trillions could create waves, currents, even colossal structures on scales dwarfing galaxies. This isn't just speculation. Some theories suggest action fields could condense into bizarre, galaxy-sized objects called Bose-Einstein condensates, where particles sync up like a perfectly choreographed dance. Picture a fog so diffuse it's invisible, yet dense enough to bend the paths of stars with its gravity. That's the paradoxical power of action dark matter, feeble individually but overwhelming in numbers. The origins of this idea trace back to an unexpected place, the subatomic world of quarks. Actions were first proposed to solve a puzzle in quantum physics. Why do the laws of nature seem to treat matter and antimatter almost perfectly symmetrically? There's a near-mirror quality to their interactions that feels too precise to be accidental. Physicists suspect a hidden mechanism, a cosmic referee enforcing this balance. Enter the action field, which would act like an invisible dial, subtly tweaking particle interactions to preserve symmetry. But here's the twist: if this field exists, its ripples could have frozen into the universe's structure during the Big Bang, leaving behind a faint, pervasive hum of actions. Detecting these phantoms is a challenge worthy of a sci-fi novel. Because actions interact so weakly, traditional particle detectors might as well be brick walls to them. Instead, scientists are building action radios, ultra-sensitive devices designed to catch the rare moments an action converts into a photon under strong magnetic fields. Projects like the Action Dark Matter experiment are hunting for these whispers in the dark, tuning their instruments like cosmic receivers searching for the right frequency. The implications are staggering. If action fields exist, they wouldn't just explain dark matter's gravitational grip. They could also unravel mysteries like why some galaxies rotate faster than their visible mass should allow, or why cosmic structures formed the way they did. Even stranger, actions might blur the line between particle and wave, behaving as both individual entities and sprawling fields simultaneously. It's a reminder that the universe's greatest secrets might not lie in the colossal or the violent, but in the quiet, the subtle, the barely there. Forces so faint we've yet to feel their touch, yet vast enough to shape the cosmos. The universe didn't just expand after the Big Bang, it exploded outward faster than light itself, inflating from a speck smaller than an atom to cosmic proportions in less than a blink. What could possibly fuel such an impossible burst of growth? Physicists call it the inflationary field, a hypothetical energy field that acted like a cosmic turbocharger, stretching spacetime at speeds that defy intuition. But here's the kicker: this field didn't just vanish. Its echoes might still linger today, woven into the fabric of reality like invisible fingerprints from the birth of everything. Think of the inflationary field as the ultimate cosmic catalyst, a surge of energy so potent it could twist empty space into a universe. In the tiniest fraction of a second, it smoothed out wrinkles in spacetime, ironing cosmic imperfections into the eerily uniform cosmos we see now. Without it, galaxies might never have clumped together, and the night sky could have been a chaotic patchwork of hot and cold spots. But once its job was done, theory says this field collapsed, dissipating its energy into the particles and radiation that filled the young universe. Yet not everyone believes it disappeared completely. Some researchers suspect traces of the inflationary field might persist, not as the unstoppable force it once was, but as a faint whisper hiding in plain sight. These remnants could take the form of ultralight particles, weaker than neutrinos, or subtle ripples in the gravitational fields between galaxies. There's even a wild possibility that inflationary energy survives in pockets of false vacuum, regions where spacetime never fully settled into its stable state, preserving a shard of that primordial power. The evidence might already be within our grasp. When scientists map the cosmic microwave background, the afterglow of the Big Bang, they spot tiny temperature fluctuations like shadows cast by the universe's earliest moments. Some of those patterns align eerily well with predictions from inflation models, as if the field left its signature in the sky. Other clues could come from gravitational waves, the ripples in spacetime from violent cosmic events. Certain frequencies of these waves might carry imprints of inflation's final moments, a cosmic echo waiting to be heard. But the most tantalizing idea: the inflationary field might not be a one-time fluke. Some models suggest it, or something like it, could activate again, triggering another runaway expansion in the distant future. Picture a universe where spacetime doesn't just expand but erupts anew, birthing fresh cosmic realms beyond our own. It's a humbling thought. The force that jump-started reality might still be out there, dormant but not dead, holding the keys to the next great cosmic chapter. What if dark energy isn't a fixed force, but something that morphs and adapts, like a cosmic chameleon, changing its behavior depending on where it is? That's the radical idea behind chameleon fields, hypothetical entities that could solve two mysteries at once: why dark energy is so elusive, and why gravity seems to play by different rules on cosmic scales. Unlike traditional fields, which act uniformly everywhere, chameleon fields would be masters of disguise, weakening or strengthening their influence based on their surroundings. Picture a stealthy shapeshifter. In the emptiness of deep space where matter is scarce, a chameleon field might grow powerful, stretching spacetime and accelerating the universe's expansion. But near massive objects like galaxies or stars, it could dampen its effects, blending into the background so thoroughly that our instruments miss it entirely. This isn't just a clever trick. It's a potential explanation for why dark energy's signature is so faint in our local cosmic neighborhood, yet overwhelming in the void between galaxies. The field isn't vanishing, it's hiding in plain sight, adjusting its grip on reality like an invisible hand tightening or loosening its fist. The real magic lies in how these fields could tweak gravity itself. Einstein's theory of general relativity has passed every test we've thrown at it, but on the scale of entire galaxies, something feels off. Stars orbit faster at the edges of galaxies than they should, as if tugged by unseen mass. Most scientists chalk this up to dark matter, but chameleon fields offer another possibility. What if gravity isn't constant everywhere? In this scenario, the field's presence could subtly alter how gravity operates in low-density regions, bending the rules just enough to match observations. No dark matter required. Testing this idea isn't easy. If chameleon fields are as slippery as their namesake, they'd actively evade detection, masking their signals in high-density environments like Earth. But physicists have devised ingenious experiments to flush them out. By measuring the infinitesimal gravitational forces between ultra-precise pendulums in vacuum chambers, or studying how light bends around massive galaxy clusters, researchers hunt for tiny anomalies that might betray the field's presence. Even the motion of atoms in quantum sensors could reveal its whispers if the experiments are sensitive enough. The implications are mind-bending. If chameleon fields exist, they'd rewrite our understanding of fundamental forces, revealing a universe where the laws of physics aren't rigid, but fluid, shaped by an invisible, adaptive medium we're only beginning to sense. It's a reminder that the cosmos might not just follow rules, but play with them, bending and twisting reality in ways we've yet to imagine. When gravitational waves ripple through space-time, they don't just pass through and vanish, they might leave behind an invisible fingerprint, a hidden structure woven into the fabric of the universe itself. These aren't just fleeting vibrations, they could generate persistent tensor fields, geometric imprints that linger long after the initial wave has faded. Think of it like tossing a pebble into a pond. The splash sends out ripples, but what if, after the water settles, the pond retains a subtle, structured pattern etched into its surface? That's the tantalizing possibility with gravitational wave tensor fields, a cosmic memory encoded in the geometry of spacetime. Gravitational waves are already revolutionary. Detected for the first time in 2015 by LIGO, these ripples confirmed Einstein's century-old prediction and opened a new window into the cosmos. But most research focuses on the waves themselves, their origins in colliding black holes or neutron stars, their frequencies, their propagation. Fewer have asked what happens after. If spacetime isn't just a passive backdrop but an active medium, could these waves deform it in ways that persist? Tensor fields, mathematical constructs that describe how spacetime stretches and twists, might hold the answer. Unlike scalar fields like the Higgs, which assign a single value to every point in space, tensor fields capture direction and magnitude, mapping the intricate ways gravity warps reality. Here's where it gets speculative and thrilling. Some theories suggest these residual tensor fields could act like cosmic recording devices. Imagine a black hole merger billions of years ago. The gravitational waves it emitted have long since passed Earth, but the tensor fields they generated might still linger, subtly altering how subsequent waves travel. Future detectors, sensitive enough to pick up these distortions, could reconstruct details about ancient cosmic events we thought were lost to time. It's like finding echoes of a scream in the walls of a canyon long after the sound has faded. Even wilder is the idea that these fields might encode information about dimensions beyond our own. String theory posits that gravity could leak into higher dimensions, weakening its force in our observable universe. Tensor fields from gravitational waves might bear scars of that leakage, hints of extra dimensions curling and uncurling at scales too tiny to see directly. Experiments like LISA, the upcoming space-based gravitational wave observatory, could hunt for anomalies in wave patterns, tiny deviations that betray the presence of these hidden structures. But the most immediate clue might come from pulsars. These ultra-precise cosmic clocks send radio waves to Earth with metronomic regularity. If passing gravitational waves leave behind tensor fields that warp spacetime en route, those signals could arrive slightly scrambled, their rhythms perturbed in telltale ways. Projects like NanoGrav are already sifting through pulsar timing data for signs of such distortions, potentially uncovering a background hum of tensor fields stretching across the galaxy. What's at stake isn't just another layer of physics, it's a paradigm shift. If tensor fields from gravitational waves exist, they could turn spacetime into a dynamic archive, preserving secrets of the universe's most violent events long after the explosions fade. From unraveling the nature of dark matter to probing the existence of higher dimensions, these hidden geometric fingerprints might be the next great frontier in our quest to decode the cosmos. And the tools to find them, they're already listening. Dark energy might not be the uniform, unchanging force we once assumed instead. It could be something far more dynamic, a cosmic presence that shifts and evolves like a living thing. This is the essence of quintessence, a theory proposing that the accelerating expansion of the universe isn't driven by a static cosmological constant, but by a rolling scalar field, an invisible energy that ebbs and flows over time. Unlike the steady hum of dark energy, quintessence would be restless, its strength waxing and waning like the phases of the moon, subtly altering the fate of the cosmos itself. Picture a ball rolling down a hill, but the hill keeps changing shape, sometimes steep, sometimes shallow. That's quintessence in action. As this hypothetical field evolves, its energy density could decrease, increase, or even flip signs, causing the universe's expansion to speed up, slow down, or reverse course entirely. It's a radical departure from the idea of dark energy as a fixed backdrop, offering a universe where the rules aren't just written but constantly rewritten. The clues for this lie in the cosmos itself. When astronomers measure the expansion rate of the universe, they find slight discrepancies, tiny mismatches between predictions and observations that a static dark energy can't fully explain. Quintessence, with its adaptable nature, could account for these anomalies. Imagine a universe where dark energy was weaker in the past, allowing galaxies to cluster more densely before strengthening in later epochs to drive the accelerated expansion we see today. This would leave faint fingerprints in the large-scale structure of the cosmos, subtle wrinkles in the distribution of galaxies that telescopes like Euclid and the Vera Rubin Observatory are now hunting for. But quintessence isn't just about filling gaps in data. It could redefine reality's boundaries. If this field exists, it might interact with other fundamental forces, coupling with electromagnetism or even neutrinos in ways that leave detectable traces. Some models suggest it could generate ultra-light particles, while others propose it's tied to extra dimensions, its fluctuations echoing from unseen realms. The most dramatic possibility, quintessence might not just accelerate expansion but eventually reverse it, pulling the universe back toward a big crunch or triggering cycles of cosmic rebirth. Yet for all its promise, quintessence remains elusive. Detecting a field that subtly tweaks the universe's expansion requires precision beyond our current tools. Scientists scour the cosmic microwave background for patterns, study distant supernova for hints of changing expansion rates, and even probe quantum vacuum fluctuations for signs of this hidden actor. The challenge is immense, but if confirmed, quintessence would reveal a cosmos far more fluid and alive than we ever imagined, where even the vacuum of space thrums with unseen change, quietly steering the destiny of everything. We've mapped the universe in 3 dimensions: length, width, height, but what if that's only a fraction of the full picture? String theory whispers of hidden dimensions curled up so tightly they're invisible to our eyes, yet vast enough to host entire landscapes of unseen fields. These aren't just mathematical quirks. They could be the missing link between the forces we understand and the mysteries we can't explain, with bulk fields bleeding into our reality like light seeping through a cracked door. Picture a spiderweb stretched across a window. From a distance, it looks flat, two-dimensional, but up close, you see the threads extend into the air, connecting in ways the initial view concealed. Our universe might be like that web, appearing three-dimensional while anchored to something far larger. In string theory's framework, the bulk is the higher dimensional space where our four-dimensional spacetime floats like a sheet of paper in a vast room. And here's the twist: fields permeating that bulk could influence our world without us ever noticing their true origin. Gravity, for instance, might seem weak because it's not confined to our dimensions. It leaks into the bulk, diluting its strength where we can measure it. These hidden fields wouldn't just tweak gravity. They could be the architects of phenomena that defy conventional physics. Imagine a scenario where dark matter isn't a particle but a shadow cast by interactions in higher dimensions. Particles moving through the bulk might imprint gravitational effects on our universe, leaving the illusion of invisible mass tugging at galaxies. Or consider the hierarchy problem, the puzzling weakness of gravity compared to other forces. Bulk fields could provide an elegant answer. What if electromagnetism and the nuclear forces are trapped in our dimensions while gravity spills into others, making it appear fainter by comparison? The implications get wilder. If bulk fields exist, they might enable effects that look like magic in our limited view. Warp drives, often relegated to sci-fi, could become theoretically plausible if we learn to manipulate higher dimensional fields to bend spacetime in ways that seem impossible in 3 dimensions. Even quantum entanglement's spooky action at a distance might find an explanation, particles appearing instantly connected because they're linked through shortcuts in the bulk, like tunnels through a mountain we can't see. Detecting these hidden dimensions isn't just a pipe dream. Particle colliders like the Large Hadron Collider could reveal their presence by producing microscopic black holes that evaporate instantly, a telltale sign of gravity's higher dimensional leakage. Or gravitational wave detectors might catch anomalies in ripple patterns, subtle distortions hinting at unseen geometries. Some theories even suggest that precise measurements of subatomic particles could uncover tiny deviations in their behavior, as if they're brushing against dimensions beyond our perception. The beauty of this idea lies in its audacity. It challenges us to rethink not just the universe's structure, but the very nature of reality. If bulk fields are real, then every law we've taken as fundamental might be a local ordinance rules that apply to our tiny corner of existence, while a grander symphony plays in dimensions we've yet to explore. It's a humbling reminder that the cosmos might be far stranger, far more layered than our 3-dimensional senses could ever perceive. Magnetic monopoles sound like something ripped from a sci-fi novel. Single, isolated poles of magnetism wandering the cosmos, unpaired from their usual opposites. In our everyday world, magnets always come with both a north and south pole. Snap a bar magnet in half, and you don't end up with 2 isolated poles. You get 2 smaller magnets, each with their own pair. But what if nature allows exceptions? What if somewhere in the universe particles exist that carry just one magnetic charge, untethered from the other? The implications would rewrite physics as we know it, warping the very geometry of spacetime itself. These hypothetical particles aren't just curiosities. They could be relics from the universe's earliest moments, forged in the extreme heat of the Big Bang when fundamental forces were still merging into one. Theoretical models suggest that as the cosmos cooled, symmetry-breaking transitions like water freezing into ice might have trapped defects in the fabric of reality, creating topological knots of pure magnetic charge. These knots would be monopoles, not just particles but singular distortions in the universe's underlying field structure. And their existence would open doors to phenomena we've never witnessed, from twisted spacetime configurations to entirely new forms of energy. Imagine a monopole drifting through space. Unlike ordinary magnets, its field wouldn't loop back on itself. It would radiate outward in a radial pattern, like the electric field around a charged particle. This unidirectional flow would create a unique distortion in spacetime, bending light and warping the paths of nearby particles in ways a dipole magnet never could. Some theories even suggest clusters of monopoles could form exotic structures, cosmic filaments, or domain walls where spacetime itself takes on strange, non-Euclidean geometries. Here's where it gets wilder. If monopoles exist, they might interact with other hidden fields in ways that amplify their effects. Certain grand unified theories propose that monopoles could catalyze proton decay, transforming matter into energy on contact. Others speculate that their presence could stabilize wormholes, threading spacetime with shortcuts between distant regions. Even dark matter might have a connection. Some models suggest monopoles could be heavy enough to account for missing mass, their gravity shaping galaxies while their magnetic fields remain invisible to our telescopes. The hunt for these elusive particles is already underway. Experiments like MOEDL at CERN scour particle collisions for traces of monopole creation, while cosmic ray detectors monitor the skies for telltale ionizing trails. Some researchers even propose that ancient minerals deep underground might hold fossilized monopoles, trapped like insects in amber from cosmic ray strikes over millennia. But the most tantalizing possibility, monopoles might not just reshape our understanding of fields. They could redefine spacetime's topology. In the presence of these particles, the universe's fabric might develop quirks where parallel lines no longer stay parallel, where angles in triangles don't add up to 180 degrees, and where the very concept of distance becomes fluid. It's a reminder that the cosmos might hide structures far stranger than we've dared to imagine, structures where magnetism, unshackled from its usual pairs, weaves the invisible scaffolding of reality itself. Phantom energy fields sound like something from a horror story, an invisible force so destructive it could tear the universe apart atom by atom. Unlike dark energy, which gently pushes galaxies apart, phantom energy would be an unstoppable cosmic bulldozer, accelerating expansion until even atoms can't hold together. The culprit, negative kinetic energy, a bizarre property that defies our everyday intuition. Normally, energy is positive, it makes things move, glow, or explode. But phantom fields flip the script, behaving like a cosmic debt that spacetime itself must repay, with catastrophic consequences. Picture a car rolling downhill, gaining speed as gravity pulls it forward. Now imagine that same car somehow accelerating backward, up the hill without any engine or external push. That's the essence of negative kinetic energy. In phantom field theory, this isn't a glitch, it's the driving mechanism. As the field permeates spacetime, its energy density doesn't just stay constant or decrease over time, it grows relentlessly. The more the universe expands, the stronger the phantom field becomes, creating a feedback loop of runaway destruction. Stars, planets, even atomic nuclei would eventually be stretched beyond their breaking points, disintegrating into a sea of lonely particles hurtling into an ever-darkening void. The math behind this scenario is as chilling as it is elegant. Phantom energy's equation of state, a measure of its pressure-to-density ratio, would be less than -1, a value so extreme it violates the so-called null energy condition, a bedrock principle in general relativity. Normally, matter and energy obey certain cosmic speed limits, like how gravity waves propagate at light speed. But phantom fields would effectively punch through those limits, warping causality itself. Some models suggest this could lead to spacetime fractures, rips, where the fabric of reality literally comes undone, not just expanding but splitting apart at the seams. What's truly unsettling is the timeline. If phantom energy exists, the Big Rip might not be some distant, abstract threat. Depending on the field's strength, it could unravel the cosmos in as little as 20 billion years, a blink in cosmic terms. First, galaxy clusters would be torn apart, their gravitational bonds overwhelmed. Next, individual galaxies would fly apart, then solar systems, until finally, in the last horrifying minutes, atoms themselves would be shredded into quarks and leptons. The universe wouldn't just fade into cold isolation, it would end in a violent crescendo of disintegration. Is there any silver lining? Strangely, yes. The sheer extremity of phantom energy makes it a useful test case for the limits of physics. If we ever detect signs of it, perhaps through precise measurements of the universe's accelerating expansion rate, it would force a radical rewrite of quantum field theory and relativity. Some researchers even speculate that phantom fields could be linked to higher dimensions or exotic matter, offering clues to unification theories that currently elude us. For now, though, phantom energy remains a terrifying what if. It's a reminder that the universe's fate isn't just about slowing down or cooling off. It could be far more dramatic, more violent than we ever imagined. And somewhere in the voids between galaxies, if this field lurks unseen, the countdown to the ultimate cosmic catastrophe might already be ticking. Even in the deepest vacuum of space, where nothing seems to stir, the universe hums with an unfathomable energy. This isn't just emptiness, it's a seething quantum froth, where particles flicker in and out of existence so fast they defy measurement. Scientists call this phenomenon zero-point energy, the baseline vibration of reality itself, and it might hold the key to unlocking fields and forces we've yet to harness. The idea stems from a fundamental quirk of quantum mechanics: uncertainty. At the tiniest scales, particles can't sit perfectly still. Instead, they jitter unpredictably, a consequence of the universe's refusal to let anything, even so-called empty space, settle into absolute quiet. This eternal churn means every cubic centimeter of vacuum, no matter how empty it appears, crackles with energy. Calculations suggest that if you could tap into just a coffee cup's worth of this zero-point energy, you'd have enough to boil Earth's oceans. The staggering part: we don't yet know if this energy is just a mathematical quirk, or if it's something we could one day manipulate. Some theories propose that zero-point fluctuations aren't just background noise but could generate detectable fields, rippling through space-time like invisible currents. Imagine an engine that doesn't burn fuel but instead rides these quantum waves, extracting energy from the fabric of reality itself. Far-fetched, maybe. But consider the Casimir effect, where two metal plates placed nanometers apart in a vacuum are pushed together by the sheer pressure of virtual particles outside them. It's proof that zero-point energy has real, measurable effects, and if we can observe it, might we eventually control it? The technological implications are dizzying. A civilization that mastered zero-point fields could revolutionize energy production, rendering fossil fuels and even nuclear reactors obsolete. Spacecraft might harness these fluctuations for propulsion, bending the quantum vacuum to achieve thrust without expelling mass, a concept NASA EagleWorks lab has tentatively explored. Even timekeeping could leap forward. Atomic clocks already rely on quantum vibrations, but zero-point precision might unlock clocks accurate to a second over the age of the universe. Yet skeptics warn of insurmountable hurdles. Extracting usable energy from the vacuum might violate thermodynamics, like trying to power a car by siphoning gasoline from a sealed tank. Others caution that tampering with zero-point fields could destabilize spacetime, creating unintended distortions or even microscopic black holes. And then there's the sheer scale of the challenge. The energy is everywhere, but capturing it would require engineering on a quantum level where the rules are more suggestion than law. Still, the allure persists. If hidden zero-point fields exist, they could rewrite our understanding of energy, revealing a universe where the void itself is a boundless reservoir of power. From warp drives to limitless clean energy, the possibilities ignite the imagination. The question isn't just whether we can harness this energy, it's whether we're bold enough to try. Einstein's gravity bends spacetime like a trampoline sagging under a bowling ball. But what if that fabric isn't just warping? What if it's twisting too? That's the wild premise behind torsion fields, hypothetical spirals in the geometry of reality that could quietly steer everything from quantum particles to the fate of black holes. Unlike the familiar curvature of general relativity, torsion suggests spacetime doesn't just dip, it corkscrews, adding a hidden spin to the cosmos that might rewrite the rules we thought were set in stone. Picture a strand of DNA, its double helix coiled tight with information. Now imagine spacetime itself has a similar twist, an intrinsic rotation woven into its structure. This isn't just poetic imagery. Torsion fields emerge naturally in certain extensions of Einstein's equations, particularly in theories like Einstein-Cartan gravity. Here, particles with quantum spin like electrons twirling like tops don't just move through spacetime. They actively wrench it, imprinting microscopic spirals that could ripple outward, altering gravity's behavior on cosmic scales. The implications are profound. If torsion exists, it might explain why galaxies rotate faster than predicted without invoking dark matter. Just as a twisted rope stores energy, torsion fields could generate extra gravitational effects, mimicking the pull of unseen mass. Even stranger, these twists might bridge quantum mechanics and gravity, two domains that famously refuse to play nice. Quantum particles exhibit spin as a fundamental property, but general relativity treats spacetime as smooth and spinless. Torsion could be the missing link, a geometric handshake where particle spins not spacetime itself, blending the quantum and cosmic into a single, twisted tapestry. Experiments are already hunting for these phantom twists. Ultra-precise gyroscopes in space, like those aboard the Gravity Probe B mission, measured spacetime's drag around Earth with unprecedented accuracy. While results aligned mostly with classical relativity, some anomalies linger, tiny deviations that could hint at torsion's subtle grip. Other proposals suggest studying neutron stars, where insane densities might amplify torsion effects, or probing the aftermath of black hole collisions for gravitational wave signatures that don't quite fit Einstein's mold. But the wildest possibility, torsion fields might not just twist spacetime, they could store information in those coils like cosmic hard drives. Some theories suggest that near a black hole's singularity, where gravity and quantum effects collide, torsion could prevent information from vanishing entirely, offering a loophole in the infamous information paradox. It's a radical idea that the universe's deepest secrets aren't written in gravity's dips or particle collisions, but in the invisible spirals hiding in plain sight, waiting for us to decipher their code. What if the glow of consciousness isn't just a biological fluke, but a whisper from the universe itself? Some scientists speculate that living cells might communicate through biophotons, ultra-faint light emissions detectable in plants, animals, and even human brain. These tiny pulses, weaker than a firefly's flicker, could hint at a hidden quantum field bridging biology and the cosmos, a frontier where the boundaries between mind and matter blur into something extraordinary. Take the human brain, a 3-pound universe of firing neurons. Standard biology explains thought as electrical impulses racing along synapses, but experiments reveal something stranger. Neurons also emit biophotons, subtle bursts of light in the visible spectrum. These aren't random noise. Studies suggest they might sync with brainwave patterns, sparking theories that consciousness could have a photonic component, a silent language of light woven into our neural fabric. Imagine if your thoughts weren't just electrochemical signals, but ripples in a field that permeates reality itself. The implications spiral outward. Plants like sunflowers don't just grow toward sunlight. They exchange biophotons with each other, almost as if engaged in a covert botanical conversation. Even DNA emits light when damaged, as if signaling distress through this quantum medium. Such observations lead some researchers to propose a biofield, a living matrix where organisms interact not just chemically, but through an exchange of quantum information. It's a controversial leap, but if true, it would mean life isn't just reacting to the universe, it's actively participating in its hidden architecture. Critics dismiss this as fringe science, and for good reason. Detecting biophotons is one thing, proving they orchestrate consciousness or cellular communication is another. The signals are achingly faint, drowned out by ambient noise, and replicating experiments under controlled conditions remains a challenge. Yet the tantalizing parallels persist. Quantum coherence, the same phenomenon that allows particles to exist in multiple states at once, has been observed in photosynthesis, where plants achieve near-perfect energy transfer efficiency. Could evolution have stumbled upon quantum tricks we're only beginning to decode? The wildest theories go further, suggesting biophoton fields might connect to larger cosmic phenomena. If consciousness taps into quantum vibrations, could it interact with spacetime's fundamental fields? Near-death experiences, meditation-induced brainwave coherence, even placebo effects, might these be glimpses of biology's entanglement with deeper layers of reality? It's a dizzying thought that the spark of awareness in your skull right now might be part of a vast, luminous network humming beneath the surface of everything. For now, the debate rages. Mainstream science demands rigor, and rightly so. But history whispers caution too often. Today's heresy becomes tomorrow's textbook. Whether biophoton fields are a footnote or a revolution remains unseen. Yet the mere possibility reframes life's deepest mystery, not just how we think, but where, in the grand tapestry of fields and forces, our thoughts truly reside. Time crystals sound like something from a physicist's dream, structures that don't just repeat in space like the lattice of a diamond, but in time itself, ticking like cosmic clocks immune to entropy's decay. First proposed in 2012 by Nobel laureate Frank Wilczek, these bizarre phases of matter defy one of nature's most sacred rules, equilibrium. Everything in the universe, from a cooling cup of coffee to dying stars, tends toward disorder. But time crystals, they dance to a different rhythm, oscillating between states indefinitely without losing energy, as if etching their own rules into the fabric of reality. How does this magic work? Imagine a snowflake that doesn't just sit frozen but morphs its shape every few seconds, returning to its original form in a perfect loop forever. That's the essence of a time crystal. Unlike ordinary matter, which settles into stillness when cooled to absolute zero, these structures maintain motion, their atoms flipping in a synchronized cycle powered not by external energy but by the quantum equivalent of a perpetual motion machine. It's as if time itself becomes a playground, with the crystal's behavior locked into a repeating sequence that even the universe's push toward chaos can't disrupt. The secret lies in what physicists call broken time translation symmetry. Normally, the laws of physics look the same no matter when you observe them. An experiment today should yield the same result tomorrow. But time crystals break this symmetry, choosing specific moments to repeat their patterns, like a metronome that only ticks at intervals it decides. This isn't just theoretical. In 2017, researchers created the first time crystals in labs using chains of ytterbium atoms and supercharged quantum computers, their rhythmic pulsing detectable even at microscopic scales. What's thrilling is the implication for hidden fields. Some theories suggest time crystals might be tapping into a deeper periodic field, a background hum of reality that oscillates in ways we've never noticed. Picture the universe as a grand orchestra with familiar fields like electromagnetism playing the melody. Time crystals could be sensing the percussion section, a rhythmic undercurrent that only reveals itself to matter structured just right. If true, this could open doors to technologies that harness these cycles, from quantum computers that never decohere to sensors that detect distortions in time itself. The wildest possibility, time crystals might be more than lab curiosities. They could exist naturally in extreme cosmic environments. Neutron stars with their insane densities and magnetic fields, or the swirling vortices near black hole horizons, might host these temporal oddities, their atoms locked in eternal dances. Some even speculate that dark matter could consist of primordial time crystals, frozen relics from the early universe whose rhythmic pulses shape galactic structures in ways we've yet to decipher. For now, time crystals remain a tantalizing glimpse into physics' frontier. They challenge our deepest assumptions about time, energy, and order, hinting that the universe's hidden fields might not just be static or chaotic, but rhythmic, beating in sync with a cosmic drum we're only beginning to hear. The holographic principle turns reality inside out. What if the three-dimensional world we experience is just a projection, a cosmic illusion painted onto a distant two-dimensional surface? At first glance, it sounds like science fiction, but this idea emerges from the cutting edge of black hole physics, where theorists stumbled onto something startling. All the information needed to describe a volume of space might be encoded on its boundary, like a DVD storing a movie we mistake for reality. And if that's true, then hidden fields could be the invisible artists etching the complexity of our universe onto a canvas we can't yet see. Think of a hologram, those shimmering images where flat surfaces create the illusion of depth. Now scale that up to cosmic proportions. The mathematics suggests that the information describing every particle, every force, even your thoughts right now, could be smeared across some unimaginably distant horizon, perhaps the edge of the observable universe itself. This isn't just abstract geometry. Fields vibrating on that faraway surface might generate the physics we experience here, like ripples on a pond's surface conspiring to create shapes in the water below. Black holes offered the first clue. When matter falls into one, it vanishes from our universe, but its information, the quantum states that defined it, can't simply disappear. Stephen Hawking's paradox shook physics until researchers realized that information might linger on the event horizon, the black hole's point of no return, imprinted like a fingerprint. Extend this logic outward, and the entire cosmos could operate the same way. The gravity we feel, the light we see, even the passage of time might be shadows cast by fields vibrating on a remote, two-dimensional screen. What's electrifying is how this reshapes our understanding of hidden fields. Instead of permeating three-dimensional space, some fundamental forces might live on that boundary, their effects bleeding into our world like echoes. Take gravity. In this framework, it could be an emergent phenomenon, not a fundamental force but a side effect of entanglement between surface-level quantum bits. Even dark energy's acceleration might trace back to interactions on that distant plane, a glitch in the cosmic projection making space itself expand. Experiments are already testing these ideas. Fermilab's holometer hunts for quantum fuzziness in spacetime, tiny fluctuations that could betray the pixelated nature of reality. Meanwhile, simulations of quantum systems show holographic behavior, with 3D effects emerging from 2D data. The wildest implication: if the holographic principle holds, our perception of depth, of distance, even of individuality, might be a grand illusion, a tapestry woven by fields we've yet to fully comprehend, painting reality from the shadows of a hidden dimension. Einstein taught us that gravity is the curvature of space-time. Mass bends the fabric of reality, and objects follow those bends like marbles rolling on a stretched sheet. But what if gravity isn't fundamental at all? What if it's an illusion, a side effect of something deeper happening at the smallest scales of reality? That's the radical idea behind emergent gravity, a theory that flips our understanding upside down by suggesting gravity isn't a force in its own right, but a collective behavior emerging from the chaos of countless microscopic interactions, like the way temperature arises from the jostling of atoms. Picture a busy city street from high above. You don't see individual people, just flows and patterns, crowds moving like rivers. Emergent gravity proposes that space-time itself behaves similarly. At the quantum level, hidden fields or information bits interact in ways we can't directly observe, but on large scales, their collective behavior gives rise to what we perceive as gravity. It's as if the universe is performing a magic trick, making something as vast as planetary orbits appear from rules written in an invisible, microscopic language. The math behind this gets even wilder. Some versions of the theory tie gravity to entropy, the universe's tendency toward disorder. Just as heat naturally flows from hot to cold, these models suggest gravity might be a kind of entropic force, a statistical nudge that emerges when systems try to maximize their disorder. Imagine spacetime as a grid of tiny pixels, each holding a bit of information. When matter disturbs this grid, the pixels rearrange to maintain maximum entropy, and that reorganization could manifest as the pull we call gravity. This isn't just philosophical musing. Observations of galaxies show discrepancies in how gravity behaves at vast scales. Stars orbit faster than Einstein's equations predict, a problem usually chalked up to dark matter. But emergent gravity offers an alternative. What if there's no invisible matter? What if gravity simply operates differently in these regimes because the underlying microscopic rules start to dominate? It's a controversial idea, but one that could explain galactic rotations without invoking mysterious, undetected particles. Critics argue that emergent gravity struggles to replicate all the successes of general relativity, like predicting the bending of light around massive objects. Yet experiments continue to test its predictions, and if even partly correct, the theory could revolutionize physics, revealing gravity as a cosmic mirage, a shadow cast by hidden fields we're only beginning to glimpse. It's a reminder that the universe's greatest forces might not be forces at all, but echoes of something far stranger. Supersymmetry isn't just a clever tweak to particle physics. It's a cosmic puzzle piece that could snap into place and suddenly make the entire picture clearer. The idea is deceptively simple. For every known particle in the universe, there's a hidden twin, a heavier, shadowy counterpart lurking just beyond our current detection. Electrons would have selectrons, quarks would have squarks, even the Higgs boson might have a Higgsino. These aren't just hypothetical placeholders. If they exist, they could explain why the universe looks the way it does, from the weight of particles to the unsettling dominance of matter over antimatter. The math behind this is elegant. Quantum fields, which give rise to particles, would extend into a mirror realm where every Fermion particles like electrons and quarks that make up matter pairs with a boson and vice versa. Fermions are the introverts of the particle world, keeping to themselves, while bosons are the extroverts, carrying forces like photons do for electromagnetism. Supersymmetry bridges these two families, suggesting an underlying symmetry so profound it could unify physics at energies we've yet to reach. One of the biggest mysteries supersymmetry might solve is the hierarchy problem, why gravity is so laughably weak compared to other forces. At the quantum level, particles interact with the Higgs field to gain mass, but these interactions should, in theory, drive the Higgs energy to impossibly high levels, making particles far heavier than they are. Supersymmetric fields act as a cosmic counterbalance. For every particle pushing the Higgs one way, its superpartner pulls back, stabilizing the system like invisible hands steadying a wobbly table. Without this symmetry, the universe as we know it shouldn't exist. Particles would either be too massive to form atoms or so light they'd zip away at light speed. Then there's dark matter. If supersymmetry is real, the lightest superpartner, like the neutralino, could be stable, electrically neutral, and massive enough to account for the invisible glue holding galaxies together. These particles wouldn't interact with light, making them perfect dark matter candidates, ghosts weaving through the cosmos, their gravity the only trace of their presence. Yet after decades of searching, we haven't found a single superpartner. The Large Hadron Collider has probed energy levels where these particles should have appeared, only to come up empty. Some theorists argue we've missed them because they're heavier than expected, or perhaps they decay too quickly to spot. Others suggest supersymmetry might manifest in ways we haven't yet imagined, broken symmetries, or hidden sectors where these fields interact differently than our models predict. The stakes couldn't be higher. If supersymmetric fields exist, they'd rewrite the standard model, offering a bridge to quantum gravity and perhaps even string theory's higher dimensions. If they don't, physicists face a cosmic dead end, forced back to the drawing board to explain why the universe seems fine-tuned for life without this elegant symmetry. Whether a triumphant breakthrough or a beautiful idea that wasn't, supersymmetry reminds us that the deepest truths of reality might still be waiting in the shadows, just beyond the reach of our colliders and detectors for now. Every second, trillions of ghostly particles pass straight through you, through the Earth itself, as if nothing were there at all. These are relic neutrinos, leftovers from the first second after the Big Bang, now cooled to a whisper of their former energy. But don't let their ethereal nature fool you. Collectively, these cosmic phantoms might form vast, invisible fields that tug at the evolution of the universe itself, shaping everything from galaxy clusters to the fate of spacetime. Neutrinos are famously elusive. Born in the nuclear furnaces of stars and the cataclysms of supernova, they barely interact with matter, sailing through planets like light through glass. Yet the oldest neutrinos, those from the Big Bang, are everywhere. Estimates suggest there are about 300 of these relic neutrinos per cubic centimeter in the universe, outnumbering protons and electrons combined. Alone, each one is vanishingly weak, but en masse their gravitational influence could be profound, like a cosmic gas so diffuse we barely notice it, yet so omnipresent it subtly steers the cosmos. Here's where it gets fascinating. Some models suggest these neutrinos might cluster in ways we can't yet detect, forming ultra-low-density fields that warp spacetime on gigantic scales. Picture a fog so thin it's invisible, yet stretched across billions of light years, its gentle gravity nudging galaxies into position over eons. These neutrino fields wouldn't rival dark matter's grip, but they could explain small anomalies in cosmic structure, why certain voids in space are emptier than predicted, or why some galaxy filaments appear slightly distorted, as if brushed by an unseen hand. Then there's their temperature. Relic neutrinos cooled as the universe expanded, and today they move at a fraction of light speed. But if even a tiny fraction was slightly heavier or slower than we think, their collective mass could alter the universe's expansion rate. It's a delicate balance. Too much mass and neutrinos would have halted cosmic growth early. Too little, and their impact fades to nothing. Remarkably, precise measurements of the cosmic microwave background hint that neutrino fields might indeed be tweaking the expansion. Their faint gravity opposing dark energies push in ways we're just beginning to model. The wildest possibility, neutrino fields might not be uniform. Quantum fluctuations in the early universe could have left some regions denser than others, creating ripples in this background sea. These ripples might imprint on the distribution of galaxies or even influence the formation of supermassive black holes, their subtle fingerprints hidden in the architecture of the cosmos. Future telescopes like the Vera Rubin Observatory could scour the sky for these patterns, searching for the faintest shadows of neutrino influence on the cosmic web. Detecting these fields directly is a staggering challenge. Current neutrino observatories like IceCube are tuned to catch high-energy neutrinos from violent astrophysical events, not the icy remnants of the Big Bang. But some theorists propose that ultra-sensitive quantum sensors, chilled to near absolute zero, might one day pick up the feeble vibrations caused by relic neutrinos streaming through Earth. Others suggest looking for anomalies in the decay rates of radioactive materials, which could fluctuate if neutrinos interact with nuclei in unexpected ways. Whether these fields exist as passive spectators or active sculptors of cosmic history, they remind us that the universe's grand story isn't just written in light and matter, but in the whispers of particles so elusive we've barely begun to hear them. And if we ever do, it could reveal a hidden layer of reality where the faintest ghosts of creation still sway the fate of all things. Cosmic strings could be the universe's most enigmatic scars, threads of pure energy thinner than an atom yet stretching across billions of light years, left over from the fiery chaos of the Big Bang. These aren't just hypothetical oddities, they might be topological defects, glitches frozen into the fabric of space-time when the fundamental fields of nature underwent sudden phase transitions, like cracks forming in ice as it freezes. Picture the early universe cooling from an unimaginably hot, symmetric state. As it expanded and cooled, the underlying quantum fields settled into their current configurations, but not everywhere perfectly. In some regions, the fields might have gotten stuck, unable to smooth out entirely, creating cosmic strings, cracks in reality where the old high-energy rules still linger. What makes these defects so fascinating is their sheer durability. Unlike ordinary matter, cosmic strings wouldn't dissipate or decay over time. They'd persist as near-indestructible filaments, vibrating like guitar strings plucked by the cosmos itself. Their energy density would be staggering. A single centimeter of string could weigh as much as a mountain, warping spacetime around it so severely that light passing nearby would bend, creating double images of distant galaxies. Some theories suggest these strings might even snap under their own tension, releasing bursts of gravitational waves powerful enough to ripple across the entire observable universe, leaving faint echoes in detectors like LIGO. But the wildest possibility, cosmic strings could have been the scaffolding for the universe's largest structures. In the early cosmos, where matter was spread nearly uniformly, these ultra-dense strings would have acted as gravitational seeds, pulling gas and dark matter into their wakes. Over billions of years, galaxies might have formed along these invisible lines, like beads strung on a necklace. It's a radical alternative to the standard model of cosmic growth, where tiny quantum fluctuations, not strings, are thought to have seeded galaxies. Yet certain anomalies in the cosmic web, like inexplicably straight filaments of galaxies or odd voids in the large-scale structure, could hint at strings' ghostly influence. The hunt for evidence is already underway. Astronomers scour the cosmic microwave background for telltale temperature spikes, sharp, linear discontinuities that could mark a string's passage. Others analyze gravitational lensing patterns, searching for the distinctive warping a string would produce, a razor-thin line where background light splits into parallel streaks. Even more speculative are proposals to detect the string's vibrations through precise pulsar timing arrays, which might catch the nanosecond hiccups in stellar clocks caused by a string's gravitational tremor as it slices through our galaxy. Yet cosmic strings pose a tantalizing risk. If one were to pass through Earth, the event would be both catastrophic and bizarre. Space itself would briefly distort along a perfectly straight line, potentially altering the distances between atoms in a way that could disrupt matter on a fundamental level. The good news, the odds are astronomically low. Strings are thought to be so far apart that the nearest one might lie well beyond our galactic neighborhood. Still, their existence would remind us that the universe isn't just governed by smooth, continuous fields, but by defects frozen into its very bones, ancient relics from a time when reality itself was still settling into shape. Whether cosmic strings are real or not, their theoretical possibility forces us to confront a universe far more textured and unpredictable than we often assume. They embody the idea that hidden fields don't just fill space, they can kink, tangle, and snap, leaving behind scars that shape everything from the tiniest particles to the grandest galactic superstructures. And if we ever find one, it would be like uncovering a fossil from the first trillionth of a second after creation, a whisper from the moment the cosmos chose its rules and left its marks behind. Quantum mechanics has always felt like a cosmic magic trick, particles popping in and out of existence, electrons in two places at once, reality itself hinging on probabilities. But what if the universe isn't as random as it seems? Enter Bohmian mechanics, a radical reinterpretation where every quantum weirdness is choreographed by hidden fields, invisible rivers guiding particles with perfect precision, turning chaos into a grand, deterministic dance. At the heart of this theory lies the pilot wave, an undiscovered field that steers particles along definite paths even when we can't observe them. Think of a surfer riding a wave. The particle is the surfer, but the wave itself is something separate, a hidden hand pushing it forward. Unlike traditional quantum mechanics, where particles exist as fuzzy probability clouds until measured, Bohmian mechanics insists they always have exact positions, just veiled by the pilot wave's influence. This isn't science fiction. It's a mathematically rigorous alternative that reproduces all the predictions of quantum theory while stripping away the randomness. The implications are staggering. For decades, the Copenhagen interpretation ruled physics, insisting reality doesn't settle until observed, a notion that troubled even Einstein, who famously argued, God does not play dice. Bohm's hidden variables offered a way out. The dice are loaded, their roles predetermined by deeper physics we've yet to map. Take the double-slit experiment, where electrons create interference patterns as if they're waves. Bohmian mechanics explains this not through superposition, but through the pilot wave's guidance, weaving particles through both slits in patterns that mimic wave behavior without ever truly being in two places at once. Critics argue the theory feels cumbersome, adding layers of complexity to explain phenomena that quantum mechanics handles elegantly. The pilot wave itself is non-local, meaning it influences particles instantly across any distance, violating relativity's cosmic speed limit. Yet supporters counter that quantum entanglement already defies locality, and Bohm's framework simply makes the strangeness explicit. More provocative is the theory's revival in modern experiments. In 2014, physicists recreated pilot wave dynamics using droplets bouncing on vibrating oil, their paths eerily mirroring quantum behavior. It's not proof, but it hints that hidden variables might not be so far-fetched. What's often overlooked is how Bohmian mechanics reframes the role of the observer. In standard quantum theory, measurement collapses reality into a single state. But in Bohm's universe, everything just is. The observer becomes part of an unbroken chain of cause and effect, no more special than any other particle guided by the wave. This erases the so-called measurement problem, offering a vision of reality where the universe isn't conjured into being by our gaze, but unfolds relentlessly, its script written in fields we're only beginning to sense. The most tantalizing question: if hidden variables exist, what shapes them? Some speculate the pilot wave could be a relic of the Big Bang, a fossilized ripple in spacetime's fabric. Others suggest it's tied to deeper layers of reality, higher dimensions, or undiscovered forces. Whatever the answer, Bohmian mechanics dares us to imagine a cosmos where uncertainty is an illusion, and every quantum leap, every entangled pair, every seemingly random decay is part of a vast, unseen order. It's a reminder that the universe's greatest magic trick might not be randomness, but the precision hiding just beneath the surface. The idea of an all-pervading ether once seemed like the key to understanding light's journey through space, until Einstein's relativity tore it apart, dismissing it as an unnecessary relic. But what if we've been too quick to bury the concept? Modern physics might be breathing new life into this old idea, not as a stagnant medium for light waves, but as a dynamic quantum field with real, measurable effects. Forget the rigid, Victorian-era ether. Today's version could be a churning sea of virtual particles, zero-point energy, and fluctuating spacetime itself, far stranger than its predecessor ever imagined. Take the quantum vacuum, for instance. Once dismissed as pure nothingness, we now know it's a frothing ocean of temporary particles and fields flickering in and out of existence. This isn't just theoretical. The Casimir effect proves that empty space exerts tangible force, pushing metal plates together as if squeezed by invisible hands. Could this be the modern ether's signature? Instead of a static backdrop, think of it as an active participant in physics, its fluctuations subtly influencing everything from the speed of light to the behavior of entangled particles. Even Einstein's relativity might accommodate this reinterpretation, not as a fixed reference frame, but as a field whose interactions are locally undetectable yet globally profound. Then there's dark energy. If the universe's accelerating expansion stems from a cosmological constant, as many believe, that constant might represent a form of ether, a uniform energy density woven into spacetime itself. Some theorists go further, suggesting dark energy could be a dynamic quantum field similar to the inflationary field that powered the Big Bang's rapid expansion. In this view, the ether isn't gone, it's evolved, its effects now measurable in the stretching fabric of the cosmos. Even the Higgs field, which gives particles mass, shares eerie parallels with historical ether concepts, acting as an omnipresent medium that particles drag through. But the most tantalizing connection lies in quantum entanglement. When particles link across vast distances, their states sync instantly, defying classical notions of locality. Bohmian mechanics, with its hidden pilot waves, offers one explanation, but another possibility is that entanglement occurs through a deeper, underlying field, a quantum ether that transmits information non-locally. Experiments like quantum teleportation and delayed choice tests hint at this invisible network, where space and time might be emergent properties of a more fundamental layer. The irony is rich. The very theory that dismantled the ether might now be pointing us back toward it, albeit in a form the 19th century couldn't have envisioned. If true, this resurrected ether wouldn't just be a historical footnote, but a bridge between quantum mechanics and gravity, between the seen and unseen. It's a reminder that sometimes the universe's boldest answers aren't new ideas, but old ones seen through fresh eyes. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most sophisticated hard drives, encoding information in ways that defy classical physics. According to the holographic principle, everything that falls into a black hole, every atom, every photon, even the faintest whisper of data, could be imprinted on its event horizon like a cosmic fingerprint, preserved not inside the singularity but on the surface, etched into spacetime itself. This radical idea turns black holes into more than destructive monsters. They become cosmic archivists, storing secrets in hidden fields that ripple across their boundaries. Think of a black hole's event horizon like the world's most extreme prison wall. In classical physics, anything crossing it is gone forever, lost to the crushing grip of the singularity. But quantum mechanics throws a wrench into that fate. Information can't just vanish, it has to go somewhere. The holographic principle suggests that as matter approaches the horizon, its quantum states get scrambled and smeared across the surface, translated into a two-dimensional code. It's like burning a book and having its ashes arrange themselves into a perfect mirror image of the text. Only here, the fire is spacetime's extreme curvature, and the mirror is a field of quantum bits vibrating at the edge of oblivion. The evidence for this lies in entropy. Black holes aren't featureless pits, they have temperature, they emit radiation, and they obey thermodynamic laws. Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy, a measure of its hidden information, is proportional to its surface area, not its volume. This bizarre math hints that the true description of a black hole's contents might live on its boundary, not its interior. If true, then black holes don't destroy information, they transform it, encoding it in holographic fields that hover just outside the point of no return. But the debate is far from settled. Some physicists argue that even if information is preserved, it's effectively irrecoverable, scrambled beyond recognition, like a DVD melted into a puddle of plastic. Others propose wilder solutions, like black holes spawning baby universes where the information escapes, or wormholes threading the data safely through spacetime's folds. The most mind-bending possibility, that the information isn't stored in any conventional field we know, but in a radically new kind of quantum geometry where spacetime itself is built from entangled bits of data. Experiments to test these ideas are as ambitious as the theories themselves. Gravitational wave observatories like LIGO hunt for subtle vibrations from black hole mergers, searching for echoes that might betray the presence of quantum structure near horizons. Meanwhile, lab-grown analog black holes, using supercooled atoms or laser beams, simulate horizon physics, offering clues about how information behaves at the edge. And lurking in the background is the AD/S/CFT correspondence, a mathematical framework where black holes in higher dimensional space perfectly mirror quantum systems on their boundaries, a tantalizing hint that the holographic principle might be more than metaphor. Whether black holes are cosmic shredders or celestial librarians, one thing is clear: their secrets stretch beyond gravity into the heart of quantum reality itself. The answers could redefine not just how we see black holes, but the very nature of information, time, and the fabric of existence. And if the holographic principle holds, then every black hole in the sky might be a shimmering hologram, its depths painted on a surface we've only just begun to decode. For centuries, physicists have chased a dream so ambitious it borders on philosophy: a single, elegant framework that explains all the forces of nature as different faces of the same underlying phenomenon. This is the promise of unified field theories, the quest to weave gravity, electromagnetism, and the nuclear forces into one cosmic tapestry. Imagine if the universe's rulebook wasn't a messy pile of separate manuals, but a slim volume where every law flowed from a shared principle. That's the vision driving theories like supergravity, where hidden symmetries might finally stitch reality's frayed edges together. Start with gravity, the odd one out. While electromagnetism and the nuclear forces play nice with quantum mechanics, gravity clings stubbornly to Einstein's geometric spacetime. Supergravity tackles this divide by introducing supersymmetry, the idea that every known particle has a hidden partner. These superpartners act as cosmic translators, bridging the quantum and gravitational realms. Picture a grand ballroom where fermions and bosons normally stick to separate corners. Supersymmetry teaches them to dance together, their steps revealing a deeper harmony that could unify all forces under one mathematical roof. But supergravity isn't alone in this quest. String theory, its flashier cousin, envisions fundamental particles as vibrating strings, with different notes corresponding to different forces. M-theory takes this further, proposing an 11-dimensional arena where strings, membranes, and gravity itself emerge from a single, higher-dimensional field. Even Einstein spent his later years hunched over equations for a unified field. Though the math of his era lacked the tools to crack it, the hurdles are immense. For one, supersymmetric particles key to many unified models remain conspicuously absent from our detectors. Then there's the hierarchy problem. Gravity is astronomically weaker than other forces, as if nature forgot to carry a zero in its calculations. Some theories suggest extra dimensions could hide gravity's strength, while others invoke exotic fields to balance the scales. Yet the payoff would be cosmic. A successful unified theory might explain why the universe prefers matter over antimatter, or how black holes preserve information. It could even hint at a deeper layer of reality, a master field from which space, time, and quantum weirdness all emerge. For now, these ideas remain equations on a page, but they whisper of a truth far stranger and more beautiful than our fragmented physics can yet describe. Why does the universe seem perfectly tailored for life? The numbers don't lie. If gravity were slightly stronger, stars would burn out too fast. If the electromagnetic force were weaker, atoms couldn't form stable bonds. Even the cosmological constant, which drives the universe's expansion, is fine-tuned to an absurd precision. Alter it by a fraction, and galaxies, planets, and life itself would never have had a chance. This eerie precision isn't just luck. It might be evidence of hidden anthropic fields, cosmic parameters locked into place by some deeper mechanism, whether a multiverse's infinite dice rolls or something far more intentional. Take the Higgs field. Its vacuum energy is mysteriously balanced to nearly zero, preventing spacetime from tearing itself apart. If it were even marginally higher, the universe would have ripped into oblivion before the first stars flickered on. This isn't a minor quirk, it's a razor's edge equilibrium that begs for explanation. The anthropic principle suggests a chilling possibility. Maybe universes where these fields aren't fine-tuned simply don't produce observers to notice. We're here because statistically, some pocket of reality had to hit the jackpot, but there's another, wilder angle. What if these fields aren't random at all? Some theorists propose that anthropic tuning points toward a feedback loop between life and the cosmos itself. Imagine consciousness as a cosmic sculptor, not in a mystical sense, but through quantum observation or some undiscovered physics where sentience subtly nudges fundamental constants. It's a fringe idea, but not without precedent. Quantum mechanics already ties observation to reality's behavior. Could that interaction scale up to the universe's very foundations? The multiverse offers a more grounded, if no less mind-bending, alternative. If infinite universes bubble into existence with every possible configuration of fields, most would be sterile voids or collapsing fireballs. Only in rare outliers like ours would conditions align for galaxies, planets, and pondering minds. String theory's landscape of possible vacuum states supports this. Every permutation of fields might exist somewhere, making fine-tuning not a miracle but inevitability. Yet even this raises thorny questions. If anthropic fields are just a statistical fluke, why do they cluster so neatly around life-friendly values? Some constants appear interdependent, as if the universe's rules were designed to converge on complexity. Others argue this is survivorship bias. We only perceive the tuning because we're its products. To test these ideas, physicists hunt for anomalies in the cosmic microwave background or variations in fundamental constants across space, seeking cracks in the facade that might reveal a grander cosmic lottery at play. Whether by accident or some deeper physics, anthropic fields force us to confront an unsettling truth. The universe isn't just allowing life, it's built for it. And that realization might be the first clue to a reality far stranger than we've dared to imagine. The vacuum of space isn't as empty as we think. It's simmering with potential energy, a precarious balance that might not last forever. What if our entire universe exists in a false vacuum state, teetering on the edge of collapse like a sandcastle waiting for the tide? This is the spine-chilling premise of vacuum decay, where a single quantum event could spawn an expanding bubble of true vacuum that rewrites the laws of physics at light speed, erasing everything we know in an instant. Picture a frozen lake on a winter morning. The ice seems solid, stable until one tiny crack triggers a catastrophic chain reaction. The Higgs field, which gives particles their mass, might exist in a similar metastable state. Calculations suggest its current energy level isn't the lowest possible, it's trapped in a false minimum, like a ball resting in a shallow valley while a deeper chasm lies just beyond the ridge. Quantum fluctuations could nudge it over the edge, creating a bubble where the Higgs field settles into its true ground state. Once formed, this bubble would expand at the speed of light, its walls carrying a new set of physical constants. Atoms gone, forces rewritten, reality as we know it, erased before we could even register the change. The math behind this isn't speculative fiction, it's grounded in quantum field theory. The Higgs potential shape, inferred from particle collider data, leaves room for this doomsday scenario. Even the sun's core temperature could theoretically catalyze the transition, though the odds are astronomically low. More unsettling, the process wouldn't require a specific cause. Like radioactive decay, it could happen spontaneously anywhere, anytime, with no warning. One moment, the universe hums along as usual. The next, an invisible wave front resets existence itself. But here's the twist, we might already be witnessing vacuum decay's aftermath. If another universe's bubble collided with ours long ago, the collision could have left imprints in the cosmic microwave background, ancient scars from a previous rewrite. Some researchers even speculate that dark energy's acceleration could be a symptom of an ongoing, ultra-slow phase transition, like watching ice melt molecule by molecule over billions of years. The silver lining, if the vacuum is metastable, it's clearly durable after 13.8 billion years. It hasn't cracked yet. and if the true vacuum exists, its physics might still permit some form of life, just under rules we can't yet comprehend. Until then, vacuum decay remains both a theoretical specter and a humbling reminder. The universe's stability might be an illusion, its permanence hanging by a quantum thread. What if consciousness isn't just a byproduct of the brain, but a fundamental feature of the universe woven into the same fabric as spacetime and quantum fields? This is the radical proposition of panpsychism, the idea that mind isn't confined to biological systems but permeates reality at every level. Picture this: electrons might not just possess charge and spin, but a rudimentary form of experience, an infinitesimal spark of subjectivity. And when billions of these particles assemble into complex structures like brains, their tiny whispers of awareness combine into the symphony of human consciousness. But here's where it gets wilder. What if these flickers of mind don't just exist passively, but actively shape the fields that govern reality? Consider the double-slit experiment, where particles behave differently when observed. The Copenhagen interpretation calls this wave function collapse, but panpsychist theories suggest an alternative. Maybe consciousness itself is the mediator, collapsing quantum possibilities into definite outcomes through its interaction with fundamental fields. It's as if the universe isn't just observed by consciousness, but responds to it like a cosmic dance partner attuned to the rhythm of awareness. Some versions of this idea propose undiscovered fields, call them qualia fields, that translate between physical processes and subjective experience, bridging the gap between the measurable and the felt. This isn't just philosophical musing. Or a controversial theory by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests consciousness arises from quantum vibrations in microtubules, tiny structures inside neurons. These vibrations could interact with spacetime's geometry, making mind a tangible player in quantum physics. Critics argue the brain is too warm and noisy for delicate quantum states, but if correct, it would mean our thoughts don't just perceive reality, they tweak its underlying fields in ways we're only beginning to imagine. Then there's the hard problem of consciousness. Why does experience feel like anything at all? Materialist science struggles to explain how biochemical reactions generate the vividness of a sunset or the sting of grief. Panpsychism flips the script. What if experience is primal, as intrinsic to matter as mass or charge? In this view, the universe isn't a cold, mechanical void, but a living lattice of subjectivity, with consciousness as the hidden variable that unifies quantum weirdness, biological awareness, and perhaps even cosmic evolution. The implications spiral outward. If consciousness interacts with fields, could collective human thought leave detectable imprints? The Global Consciousness Project claims to find statistical anomalies in random number generators during globally significant events, as if mass emotion briefly warps probability. Skeptics dismiss it as coincidence, but if fields responsive to mind exist, even at a subtle level, it would redefine everything from meditation's effects to artificial intelligence's potential for true awareness. Whatever the truth, panpsychism challenges our deepest assumptions, not just about minds and brains, but about the nature of reality itself. It dares us to consider that the universe might not just contain consciousness, but be conscious, its fields humming with the faintest echoes of inner life. And if that's true, then every star, every atom, every fleeting thought might be part of a vast, whispering dialogue between matter and mind. Forget invisible dark matter shaping the cosmos. What if the true architects of galaxies are rivers of electrified plasma, writhing through space like cosmic lightning? This is the bold claim of plasma cosmology, a fringe but fascinating theory that swaps mysterious dark matter for something we can actually see: superheated, magnetized gas threading the universe. According to this model, it's not gravity alone sculpting spiral arms and galactic clusters, but colossal electromagnetic fields generated by swirling plasma currents. structures so vast they could stretch between stars, even between galaxies, conducting the grand symphony of cosmic structure. The idea taps into a simple truth: plasma isn't rare, it's the universe's dominant state of matter. Over 99% of the visible cosmos, from the blazing hearts of stars to the gossamer strands of interstellar gas, is plasma, atoms stripped of their electrons forming a sea of charged particles. These particles don't just drift passively, they're puppeteered by electromagnetic forces far stronger than gravity over short distances. Twist a plasma into filaments, as labs do with devices like tokamaks, and you'll see them snap into braided ropes held rigid by their own magnetic fields. Scale this up to galactic proportions, and suddenly, the delicate spiral arms of the Milky Way might not need dark matter's extra gravity to stay intact. They could be sheathed in invisible electromagnetic scaffolding, their stars glued in place by currents we've yet to map. Critics argue that plasma cosmology can't fully replace dark matter after all. It doesn't explain all the gravitational anomalies we observe, like the bullet cluster, where galaxies and their gravity seem to have separated. But proponents counter that we've barely scratched the surface of plasma's large-scale behavior. In labs, plasma self-organizes into double layers and cellular structures. In space, these could form immense transmission lines channeling energy across light years. Some even suggest that quasars, those brilliant, distant beacons, might be cosmic short circuits, where intergalactic plasma currents abruptly discharge, lighting up the void like a celestial neon sign. The most tantalizing evidence comes from the cosmic web itself. Telescopes like the Hubble have revealed filaments of gas lacing the universe, and while mainstream science attributes their structure to dark matter's gravitational pull, plasma cosmology sees something else: Birkeland currents. These are twisted pairs of plasma filaments that naturally attract one another, pinching into glowing knots where galaxies might form. Sound familiar? It's eerily reminiscent of how galaxies cluster along the cosmic web's luminous strands, as if painted onto pre-existing electric brushstrokes. Of course, the devil's in the details. Plasma's electromagnetic forces weaken with distance faster than gravity, making it tricky to explain how they dominate on galactic scales without impossibly strong currents. Yet plasma cosmologists point to anomalous magnetic fields detected across the universe, mysterious forces too widespread to stem from stars or black holes alone. Could these be the faded signatures of primeval plasma rivers, their energy now thinly spread but once powerful enough to forge the cosmos? Whether plasma cosmology overturns dark matter or merely complements it, the theory forces a vital question. Have we been too quick to dismiss the electrified elephant in the room? For centuries, we've seen space as a passive stage, its actors moved by gravity's unseen hand. But what if the universe is more like a vast circuit board, crackling with currents that light the stars, sculpt the galaxies, and whisper secrets about how everything truly fits together? The answer might not lie in the darkness between the stars, but in the charged glow we've overlooked all along. Quantum entanglement is the universe's ultimate magic trick, particles separated by light years somehow mirroring each other's states instantly, as if space and time don't exist between them. Einstein famously called it spooky action at a distance, a phrase that stuck because, well, it feels like magic. But what if the spookiness isn't just a quantum quirk? What if it's the work of hidden fields, invisible threads stitching the cosmos together in ways we're only beginning to unravel? Picture two entangled electrons spinning in perfect sync, one on Earth, the other near a distant star. Measure one, and its twin flips instantly. No signal, no delay, just instantaneous correlation. Standard quantum mechanics treats this as non-local, a mathematical reality with no physical mechanism. But some theorists propose a radical alternative: entanglement fields. These wouldn't be fields in the traditional sense, like electromagnetism or gravity, but something more subtle: a background network of connections woven into spacetime itself. a kind of quantum Wi-Fi that doesn't transmit information but maintains instantaneous links between entangled particles. The idea isn't as far-fetched as it sounds. In quantum field theory, particles are excitations in underlying fields. The Higgs field gives mass, the electromagnetic field carries light. Why couldn't entanglement arise from a field too? One candidate is the quantum pilot wave from Bohmian mechanics, a hidden variable guiding particles along deterministic paths. Extend this idea, and you might imagine a universal entanglement field, a dynamic web updating particle states everywhere at once, like a cosmic game of telephone where the message skips the line and appears at both ends simultaneously. Here's where it gets even wilder. These fields might not just connect particles, they could scale up. Galaxy clusters, for instance, show large-scale structures too finely tuned for random chance. Some speculate that quantum entanglement, mediated by fields, could have imprinted patterns in the early universe, linking regions that should have never been in causal contact. It's as if the cosmos itself is entangled, its vast web of galaxies whispering to one another across the void. Detecting these fields is the real challenge. If they exist, they'd operate outside classical physics, leaving no energy signature or force to measure. But experiments with quantum networks hint at possibilities. When scientists entangle particles over fiber optic cables or even via satellite, the correlations hold, no matter the distance. Some propose that gravity's quantum nature, once understood, might reveal entanglement's field like fingerprints, perhaps through anomalies in spacetime's geometry or subtle delays in quantum computations. The implications are staggering. If entanglement fields exist, they'd blur the line between particle and universe, suggesting a reality where separateness is an illusion. From black holes preserving information on their horizons to the emergent nature of spacetime itself, these fields could be the hidden scaffolding beneath quantum mechanics' bizarre rules. And if we ever learn to map or manipulate them, that's the stuff of sci-fi dreams: quantum communication unshackled by distance, or even a new lens to view the cosmos, not as isolated points, but as a shimmering, interconnected whole. What if the fields shaping our universe, gravity, electromagnetism, even quantum fluctuations, aren't fundamental forces at all, but lines of code in an unfathomably advanced simulation? The simulation hypothesis isn't just sci-fi speculation. It's a serious argument that reality might be a construct, with hidden fields acting as algorithmic shortcuts to render physics without the computational burden of calculating every particle from scratch. Think of it like a video game. When you're playing, you don't need the software to simulate every atom in a mountain, just the ones your character interacts with. Now scale that up to cosmic proportions. The Higgs field may be just a lazy programmer's trick to assign mass without computing each quark individually. Dark energy, a patch to prevent the simulation from glitching as it expands. This isn't just philosophical noodling. Physicists have noted eerie fine-tuning in nature. Constants like the cosmological constant or the strength of nuclear forces are balanced on a knife's edge, as if dialed in by hand. Even quantum indeterminacy fits the analogy. Why calculate a particle's exact path if no one's looking? It's like a game engine only rendering graphics when the player is watching. Some theorists, like Silicon Valley mavericks and Oxford philosophers alike, argue that if advanced civilizations ever run ancestor simulations, statistical logic suggests we're more likely to be inside one than in the real universe. But here's where hidden fields enter the picture. If we're in a simulation, the universe's underlying physics might not be seamless. There could be artifacts, glitches in the matrix. Physicists have proposed tests. Look for pixelation in high-energy cosmic rays, or hunt for rounding errors in the values of fundamental constants. Others suggest probing quantum entanglement for signs of bandwidth limits, as if the simulation can't process infinite correlations. Even the speed of light might be a built-in frame rate, a processing speed limit to prevent system overload. The wildest implication: if simulation fields exist, they could be hackable. Just as a video game's physics can be modded, a simulated universe might have backdoors, undocumented variables, or exploits in its code. Some speculate that phenomena like quantum tunneling or psi effects, if real, might be users bending the rules from outside the system. Others warn that poking too hard at these fields could trigger a crash or worse, a patch that rewrites our reality overnight. Whether cosmic horror or cosmic joke, the simulation hypothesis reframes every mystery in physics. Dark matter, quantum duality, even consciousness itself might not be features of nature, but UI choices in someone else's cosmic sandbox. And if that's true, the greatest discovery wouldn't be a unified field theory, it'd be the developer's signature hidden in the math. From the quantum whispers of zero-point energy to the holographic code of black holes, these 30 theories paint a universe far stranger than we ever imagined. A cosmos where empty space hums with hidden fields, where gravity might be an illusion, and where even the laws of physics could be written in invisible ink. Each idea, no matter how speculative, challenges us to rethink reality's bedrock. Could dark energy be a chameleon field, shape-shifting across the cosmos? Might axions weave the unseen fabric of dark matter? Is spacetime itself a projection from some distant, two-dimensional edge? The beauty of these questions isn't just in their answers, but in how they stretch our minds to glimpse a grander, weirder truth, that the universe's greatest mysteries might not lie in the stars, but in the quiet, pulsing fields beneath them. This isn't just academic curiosity, it's a revolution waiting to happen. If even one of these theories proves true, it could rewrite textbooks overnight. Imagine waking up to headlines confirming torsion fields twisting spacetime, or lab-grown time crystals powering quantum computers. Picture a future where we manipulate vacuum energy like alchemists of old, or decode entanglement fields to communicate faster than light. The frontiers of physics aren't just about discovering new particles, they're about uncovering the hidden architects of existence itself. And the wildest part: we're living in the moment when these ideas leap from speculation to testable science, thanks to telescopes sharper than ever, colliders more powerful than dreamed, and simulations that bring cosmic math to life. So what's your favorite theory? The eerie fine-tuning of anthropic fields, the spine-tingling risk of vacuum decay, or maybe the bold claim that plasma currents, not dark matter, sculpt galaxies? Drop your thoughts in the comments. Let's geek out over the cosmos' best-kept secrets. And if you're hungry for more mind-bending mysteries, hit subscribe. From cosmic strings to simulated realities, we're just getting started. The universe is speaking in fields and frequencies we're only beginning to hear. Don't miss the next chapter, because the greatest discoveries aren't just out there, they're everywhere, hidden in plain sight.